Welcome to mass spectrometry. We have done a introduction and talked about how mass spectrometry works and kind of a little tour of the machine. Let's put a molecule through the machine, see what happens. Okay, let's take the simplest molecule, just an alkane, and shoot it in here into the sample area and let it, vaporize, go through that vacuum and go into that chamber. And here you go, the molecule, octane's having a really nice day, probably had a nice English breakfast with a pancake and a stack of bacon, and driving along the freeway here, da-di-da-di-da-di-da, and bam, it gets hit by this 70 electron volt lightning, okay? And one of the electrons is gone. It's leaving a hole here. So basically took off the electron. Oh, well, can you even hold it together? Well, what you really have now is like a radical and a cation. You got a hole here. That's just going to unravel the entire molecule. And that's why you're seeing so many of these molecules popping out. So the molecule then goes through, and well, all the neutral parts get sucked up through the vacuum pump, and it gets accelerated and goes through that magnetic tube and gets thrown onto that detector. It's a weak link on the chain. It's going to pull everybody out. Okay, so what we have here is a radical cation. All right, so let's say that's your molecule. You have a octane here, and the octane is coming out as a radical cation after that lightning strike. All right, so here is your radical cation. So you have a positive and a dot, and this methyl, I mean, that's like a half bond order right there. This is a hole. There's nothing here. That's why we put a positive, and there's one electron between those two. Another way to write this is just, put a radical cation outside. So this is the same as writing this molecule here as a radical cation. What happens then? Well, you can't just leave this unpaired electron alone. Something's got to happen. So this one, if you count up all the carbons and the hydrogens and put them on a weighing scale, that's going to be 114 molecular weight. AMU, because you're talking about one molecule. You're not talking about a whole mole. So it's not grams, it's AMU. All right, let's see what happens once, well, the molecule keeps going through the tube, and then while it's going through the tube, things happen to make it more stable. The molecule, the carbon next door is kind of sympathetic, and so it takes off an electron and gives it over here. Okay, so now you've literally broken that molecule in two. You have over here on this side an empty hole. You took off your electrons there and gave it over here. So here you have a cation. So basically what you're going to do is you're going to take these electrons and give it over here. And what you have then is this fragment coming off as a radical. So this has now, if you look at this, 1, 2, 3, 4, 1, 2, 3, 4. So they're all neutral, and since you have an unpaired electron there, that part is going to be the radical neutral part. The radical neutral part gets sucked up after it gets hit by the lightning. There's a tornado that just takes out your radicals, and your cations keep going. There's a negatively charged plate that's going to accelerate it, goes through this arc through, between a north and south magnet, and it's going to hit the detector. All right. So here is your fragment that's coming out. 1, 2, 3, 4, 5, and 6. This guy has got a big hole, nothing here. So the formal charge here is 4 minus 1, 2, 3 is a plus. The plus goes all the way, bam, hits the detector, and the guy there on the detector says, all right, welcome to the junkyard. We got more of you here, and you can pile up, you know, with your kind. So it puts them in the same place. As more and more of these come in, you're going to see this piling up. So then you have over here 1, 2, 3, 4, 5, 6 carbons. If you count them up and add the carbon and hydrogen weight, that's going to be 85. Okay, so from 114, you got a 29 piece out for this ethyl, and that goes through the chute, and this is what hits your detector. It's positively charged. The Z is 1. So M is 85, Z is 1, plus 1. So that's M over Z is 85. All right, so that's that peak. So so the detector just, you know, notes all the ones with the same mass. All right, says, okay, check, positively charged, mass 85, pile it on. So you get more and more of them. They're going to accumulate. The guy is going to stack them up on one on top of the other. And the more of these you get, the taller the graph. It's going to go send a signal here every time you get one, and it's all going to go at once and print it all out. So this is literally counting the number of molecules. Now here, this is your molecular ion peak, because this is just by making that positive hole here by removing one electron. So that is your positive hole, and so the mass is the same as the molecular ion, molecular weight of the octane, so the molecular ion peak. Okay, that's your first peak always, or at least the one that's noticeable. You can have a teeny M plus 1, because as we talked about before, carbon 13 is 1.1%, so you would have that peak over there for the carbon 13. And so you would have your next peak here. Well, keeps going some more, and bam, it gets hit some more. All right, what can happen after this? Well, you got a positive. You can think of this as unraveling. Well, you can take this electron and break it up some more. All right, so here's a carbon, and it's got 2 electrons, and this is going to be now your positive. Then you can break this up and take off a CH2 and a CH2 and a CH2. And if you look at this, a CH2, this is a CH2, because you can see there are 2 hydrogens, one up and one down. So if you take this CH2, the formal charge is 1, 2, 3, 4, 4 minus 4, carbons group 4, so 4 minus 4, this is 0. So this is a neutral peak that's going to go through the chute. Then you'll have a positive here, because you pulled out those electrons. It doesn't have its valence pair. If you take the formal charge of this fragment, it should be 4, but it's got only 1, 2, 3. So this is going to be your positive. So this is 12 plus 2, 14. M is 14 mass. So if you take the difference here, you will notice 85 minus 71, that is a 14. 71 minus 57, another 14. 57 minus 43, another 14. Every single time you can think of a CH2 coming out. All right. 43 minus 29, another 14. And 29 minus 15, another 14. So you can think of these CH2 units just unraveling and giving you these fragments. All right. So 43 is the most abundant, which is like, it sets it to 100%. and all of the others are measured as a relative percentage of this major peak. Okay, if this is 100, then this is about 25%, and so on. Okay, so this is a relative abundance or relative intensity. Okay, so what's 43? Well, let's look at it. 43 means if you have 3 carbons, that's 36. So probably this is a 3-carbon fragment. Now, you can think of this as, going, CH2 serially one at a time, or this is another very likely possibility, just like you hit it with a 70 electron volt lightning electron EI, electron ionization. Your molecule just goes up in energy like 1,700 kilojoules per mole and then starts unraveling. So here, just like you took this off and put a positive here, you could have done that anywhere on this chain. All right, guys, let's look at what would happen if this molecule is sauntering down the alleyway here and going over here and getting hit by that lightning or 70 electron volt electron ionization, and in different places of the molecule. Earlier, we kind of took CH2s apart. I did that mainly to show you that the reason why these are 14 apart is because these CH2s are 14. But in reality, when this molecule goes through this, the lightning or the electron ionization, it could even be chemical ionization. I mean, you can put like ammonium or H+, and those can do ionization too. But just to keep it simple, we'll talk about electron ionization. And these really, when it goes through, it can chop it anywhere here. Okay, and so that's why you're getting different peaks at different positions or masses. Okay, so if you want, let's say you have a molecule like this, CH3, CH2, CH2, and then you can see, let's say you have over here, a 3-carbon fragment. You could imagine that this could be something very similar to this. Okay, let's say you have over here, these are my son's toys, well, once upon a time. So if you take this and you rip this off, you can have a lightning hit right here instead of, at the edge. It could happen anywhere in the molecule. But here you could either have it here or here. So let's say this molecule is going along the tube, it's having a really nice time, and suddenly it gets struck by lightning, takes out that electron. So now you're going to have a positive hole here. And this is going to be your radical, and that's going to be your cation, and they just unravel, they just come apart. So here you are going to have this go over to this part, and you're going to have a fragment that is going to have a CH2 radical, and you're going to have a fragment, and I'm going to draw this out in another color, that has got a cation, which is a hole. There's no electron there. It doesn't have a filled valence. And typically, I mean, the radical tends to have a longer chain than the cation. It doesn't always have to be so, but it happens a lot of the time. And that's, you can see that's the fragment. And if you count up the hydrogens and the carbons, 36 plus 7 is going to be your 43, the king of the peaks. And you can see, when you break this up here, if you get 4 carbons, you're going to get 57. If you get 3 carbons, 43. 29 is going to be your ethyl cation, and 15 is going to be your methyl cation. Basically, you're unraveling the molecule. You took off an electron, that's the weak link. It collapses the entire molecule, and they all fall apart, and you get smaller and smaller fragments. All right, so that's pretty much an example of what the mass spec is going to look for an alkane. Now, if you have a branched alkane, you may get peaks at different places, but wherever you have branching, you tend to have more fragmentation. And I'm just going to write down the other peaks. So 15 would be if you, let's say, hit it here and your electrons moved over there, that is going to be your CH3 plus, and that's this teeny bit here. 29 is if you hit it here and your electrons moved over, and you're going to get CH3, CH2 plus. And we already talked about 43. 57 is if you hit it over here and had a 4-carbon peak. So 43 is your propyl cation, and 57 is your butyl cation. All right. 71 is when you have a 5-carbon cation. So you have an idea, I hope, of how all of these peaks are forming in a mass spec. So this is just an example of one molecule, octane. Obviously, if you put, let's say, heptane or hexane, then your peaks are going to be different because your molecular ion peak is shifted. However, in alkyl spectra, if you have an alkane, pure alkane, you are bound to see these peaks. Ethyl, if you see a 29 peak in an alkane, or if you're something that has an alkane chain, it's typically going to be an ethyl cation. If you see a 15 peak, chances are it's a methyl cation, and those are very tiny. If you see a 43, it's probably a propyl cation. 57 is a butyl cation. 71 pentyl cation, and so on. Okay, 85 hexyl cation, and so on. So the reason I'm writing these peaks down individually is because a lot of the organic molecules have long side chains, or they have a, let's say, a carboxylic acid and a long tail, a long alkyl tail, and you would see these peaks again. So if you see these peaks at these numbers, it's a good idea to remember that this could be just the unraveling of the alkyl tail or alkyl side group or the alkyl main chain. All right, so all of these have Z equals 1, okay? Because you can have peaks that are Z equals 2, but those will be very rare, because when you're going through to get struck by lightning twice, it's almost like a cliche, to get struck by lightning twice is kind of rare. So you have a Z equals 1 for all of these. So here you go. So lightning strikes and cations form, and that's what the detector is reading. The detector is just like a counter, a mass counter. It says, okay, 43 coming in, pile it on. 43 coming in, pile it on. And it just piles on whenever this fragment comes through. So since you have this coming through, it piles on and piles on, and you would get that as the maximum peak. That's called the base peak. Everything is measured against that. Relative abundance is measured against that. All right. So let's say you have 100 of these peak of 43 coming in. For every 100 of that, you only have about 25 of the ethyl cation coming over, or about 20 of these 5-carbon cations coming over. So this is just giving you a relative abundance. How many? It's just a counter, which is why we call it spectrometry and not spectroscopy. This is not absorbing radiation in a wave, in a frequency range, and showing absorption and emission. This is just counting the peaks, how many and how heavy are they. So it's almost like having a little weighing scale here, and it's going to fall on that. You're going to record the weight and the charge. M over Z is going to be what you see for these numbers here, mass over charge. All right, so we are going to look at some more spectra, and we are going to see how we can explain all of the peaks. Talk to you soon. Bye.